Okay, good afternoon. So just a really quick announcement. This is a total tangent. So apparently, sort of randomly, I heard that I might be interviewed by the New York Times about webcast lectures. I don't know how, by what strange chain that came to me, but anyway, this might happen. And so I just thought I'd throw out there, if anyone either in the class or watching the lecture from somewhere else wants to make any comments to me, feel free to send me an email. It's hank@stat.berkeley.edu. And I'm just curious as to what people might have to say. And I might, consider what people say when they talk to me. So I thought I'd like to have something to say. So if anyone has anything to say to me, that'd be great. So it'll be feedback, positive, negative, how you use webcast, if you're somewhere else, where you are, something like that. Okay, any questions about what's going on in class right now? Okay, so there will be a quiz posted next Monday, the holiday. I'll put it up then. It's due a week from then. So don't worry about it. You don't have any section on Monday. And also the homework assignment that would ordinarily be due on Monday will be due in a week. So there's sort of a double, or two assignments will be due a week from Monday. I guess that's the February 22nd, I think. Okay, any questions about that logistical stuff? Okay, so last time I finished up with chapter 10, talked about regression, what it is, how to do it intuitively, and also talked a fair amount about the regression effect. And again, sort of why that happens and kind of a little bit about how that happens. I'll often refer to that as regression to the mean. I think that describes a little bit better what's going on. And one more thing about that I usually say when I teach it, and I neglected to, is there's this, I think, there's a little bit of a paradox that goes on that makes the regression effect not very intuitive. And the paradox is that if you think about, Yao Ming's kids, sons should be shorter than Yao Ming, but still tall, right? So closer to the average. Well, then if you think about his grandkids, then you sort of think, well, they should be expected to be still tall, but closer to the average. Great grandkids, closer to the average, closer to the average. So then you sort of think, well, after a certain number of generations that have gone by, it sort of seems like everyone should be the same height somehow. If everyone's regressing towards the mean, generation after generation. And the idea is that the extremes get kind of replenished from people that are close to the mean now. So if we have a bunch of fathers that are kind of close to the mean now, there are many, many, many such fathers. In the next generation, their sons will have some variability in height. And so, sort of rarely, but sometimes, average fathers will produce extremely tall or extremely short sons. So even though the predicted heights are close to the average, the variability in heights kind of refills the extremes. So if you want to think about just a quick picture, there are a lot of fathers that are around the middle. Okay, their sons are expected to be average, meaning that the center here, the center of this strip, is at the average. But it's not like they're all average. Many of them are quite tall and quite short. So when you think of the next generation, if this is father's sons, father's heights, son's heights, the next generation will have the extremes kind of filled out because there are so many fathers near the average who have sons that are extreme. Okay? So I just wanted to mention that again. And it's also a little bit of a segue into what we're going to talk about today, which is that variability. That variability that goes on for heights. So far we've talked about the center in each vertical strip. So far regression tries to get at, well, where's the graph of averages? So, what's the average y value corresponding to that x value? The kind of natural next step is to think about the spread. If you think about kind of the way this course has run from the start, first thing we talked about was histograms, pictures. Very next thing is to talk about summary statistics, measures of center and spread especially, the average and the SD. So now, not only do we get an idea of what the center is there, but we'd like to get an idea of how much those y values are spread out again, corresponding to a particular x value. So for a particular x value, chapter 10 tells us about where those scores should be centered. Chapter 11 tells us how spread out those scores are, okay? Or those heights or whatever they happen to be. Okay, so general topic for today is how accurate is regression? And to start doing that, I'll go back to this picture. So we have all these dots here, right? All these dots all over the place in this picture. And let's just pick one up here, say. So that represents someone's actual x value, y value. So, you know, their predicted value is there. If we use regression to make a prediction, we predict that person's going to be there. So this is predicted value. And up here is their actual value. So we predict their value using regression. That tells us the center roughly in that vertical strip. And then the predicted value might be above, might be below. And the distance between those 2 points, or the difference between those 2 points, is called a prediction error. Basically just how far off the actual value is from what we predicted that it would be. And this is kind of analogous to a deviation from average. If you think about just one variable all by itself, chapter 4, you think of the average value, and then the distance from the average is called a deviation from average. So you might think that what we'd like to do is think about the RMS of these things. Just like in chapter 4, the standard deviation measures the RMS of the deviations from average. We're going to do basically the same thing here. We're going to try to figure out what the RMS of these things is. So we want RMS of deviations from average. Oh, sorry, that would be the SD. What we want is the RMS of the prediction errors. And this is called the RMS error. So it's literally what we would get if we took a prediction error for every single person in this picture and took the root mean square of those prediction errors. Okay, that's how the RMS error is defined. So getting back to regression specifically, for regression, okay, if we're doing regression, we have a formula that will work. And so in general, you maybe should be a little bit fearful at this point that I would actually make you calculate prediction errors for everybody and manually calculate RMS of those. That'd be a lot of work. If you have more than just a few data points, that's quite a bit of work because you have to predict every single value, and then you have to take the deviation, the deviation or the difference between the actual value and the predicted value, and then calculate the RMS of those. So that would be very time consuming in general. For regression, it turns out that this has a nice, simple formula. It's square root of 1 minus r squared times the SD of y. Okay. Now, when I say for regression, well, what else could you do? Everything we've done so far has been predicting y based on using regression. Okay. There's no law that says that you must do that. It turns out that that's a smart thing to do. Essentially, what that's doing is it's guessing the average y corresponding to each x, and guessing the average is sort of a smart thing to do. But you don't have to. And if you, for example, guessed the average of everybody, right? So again, regression guesses the average for everyone just like that person. So if you're predicting weight from height, if you wanted to guess someone's weight and you knew their height, well, you'd think, well, what's the average weight of everyone that height? Okay, that'd be sort of a smart thing to do. Maybe a slightly less smart thing to do would be to ignore height and just consider, well, what's the average height of everybody? So suppose instead of regression, we simply guess the average of everyone. So where would my guesses be if that's my plan? No matter what x is, I'm just going to guess the average of everybody. Can I draw a line? Like over there, I could draw a line, right? The regression line gives me all my predictions. Is there some similar thing I could do here that would give me all my predictions? Anyone? Yeah. Yeah, a horizontal line through the average is sort of the analogous thing that I might do, where this is the average of y, average of all y's, right? So suppose I make all my guesses on that line. Now let's think about what my prediction errors are. We have actual values here and there. Here's an actual value. My predicted value, according to this, this method of prediction, just always guessing the average, will give me predictions on that line, on that horizontal line through the average. And that's a prediction error, right? So what if I take the RMS of those? What would I get? Any thoughts? So the RMS error is sort of defined the same way, right? It's the RMS of these prediction errors, just like I defined there. RMS of prediction errors is called the RMS error. Yeah? Yeah, that would be the SD. So if I took the RMS error of these things, I would get the SD, because these distances are literally deviations from average, right? What I would do to calculate the prediction errors is for every point in this picture, I would take the value and subtract off the average, okay? So these are literally deviations from average. So if I take the RMS of them, I'm literally calculating the RMS of the deviations from average, which is the SD of y. So in this case, RMS error equals SDY. Okay, so like I said, this is maybe not as smart. Using regression is a little bit smarter because, especially out of the extremes here, a point on this horizontal line is not really a very good guess. I'd rather guess something halfway in between, essentially what regression would tell me, the average y value in that vertical strip. Okay, so we can compare these and make a judgment about which one of these is better, right? So which one's better? I mean, mathematically. Our RMS error is sort of a measure of how accurate our guesses are. It's sort of a typical size of prediction errors in the same way that the SD in general measures the typical deviation from average, typical distance from the average. The RMS error measures the typical prediction error, typical size of the prediction error. So if that's small, that's an indication that we're doing something kind of smart, right? If the RMS of the prediction errors is small, then it means that our predictions are pretty accurate. So which one of these is smaller in general? Yeah, this is going to be smaller in general, right? Regression is going to be doing something that is smarter than just simply guessing the average all the time. And you can tell that because of this term here, right? This is going to be less than 1 unless r is equal to 0, right? So let's think about that formula a little bit more. So special cases for the regression formula. Here's the formula again. I'll just rewrite it. Square root of 1 minus r squared times the SD of y. And let's think about what happens when r is equal to 0. So if r is equal to 0, put a 0 there. We get 1 out in front. We just get SDY. So intuitively, why should that be true? Why should we have the RMS of the prediction errors equal to the standard deviation of y when r is equal to 0? Any thoughts? Yeah.
Because when r equals 0, there's no strong correlation, so we just guess the average of everyone.
Yeah. Okay. So just saying, if r is 0, the correlation is, there's sort of no correlation. There's no relationship. Your guess would be the average of everybody, right? So if r equals 0, in fact, all your guesses are on a horizontal line through the average, just like up there, okay? If you have a high x value, you're going to guess the same thing as if you have a low x value. Doesn't matter. No matter what the x value is, you're always going to guess the average of y. So in fact, you're doing the same thing as I have up there. Just a horizontal line through the average is what you would do to make your guesses. Another way to think about it intuitively is that if r is 0, knowing x doesn't really help you. It doesn't do any better to know x as opposed to having no information at all. If you have no information at all, a sensible guess might be to just guess the average of everybody, which would give you an RMS error of SDY. Okay? So what about r is 1 or negative 1? Sort of the other extreme case. What's the RMS error in that case? It's 0, right? So if we plug in either +1 or -1 here, we square it, meaning we get 1. 1 minus 1 is 0. 0 times SDY gives us 0. Why should the RMS error be 0 in that case? Yeah, it's the perfect correlation. All the points are on a line. If the correlation is positive, if correlation is +1, then it's a line with positive slope. If the correlation is negative, it's a line with negative slope. Either way, what regression is going to do is it's going to guess points on that line. Okay? So all the points are actually on that line, meaning that all the predicted values are exactly equal to all the actual values. So the actual values equal the predicted values. All the prediction errors are 0. Take the RMS of a bunch of zeros, you get 0. Okay? So those are the sort of the two extreme cases. In general, if r is something else, then this will be somewhere between, this thing out in front will be somewhere between 0 and 1. If you have r closer to 1, the RMS error will be smaller, right? Think about putting in a 0.9 here or something like that. You're going to get a fairly small RMS error, meaning that all your predictions are pretty accurate. If the correlation is pretty close to 0, then the thing out in front is pretty close to 1, and you're not doing very much better than just guessing using a horizontal line through the average. Okay, so in between, you get something in between. Okay, any questions about that? The formula. So I'm not, proving why that formula is what it is. I'm just trying to at least explain that it makes sense in those extreme cases, and it's true, right? Okay. So. Yeah, so we'll talk more about this when we hit chapter 12, but I just want to mention that I sort of said RMS error is in some sense kind of a measure of how good your prediction method is. If you're doing regression, you get this as your RMS error. If you're doing something not as smart, like always guessing the average, the RMS error should tend to be bigger. They're the same, when the correlation is 0, but in general, regression does better. And in fact, regression has a smaller RMS error than any other line than we could draw. So I'll talk about that more in chapter 12. But again, the regression line, using the regression line for making predictions will give you the smallest RMS error of any line I could draw. Okay? So that's the reason why we do regression, is that by that measure, taking the RMS of the prediction errors, this will give us the smallest RMS of prediction errors. Regression will give us the smallest RMS of prediction errors compared to anything else you can think of. Okay, so that's why we do it. And like I say, I'll address that a little bit more in chapter 12. Okay, so I want to go back to comparing a little bit. Comparing the situations of this and regression. Let me just grab that picture again. So suppose I do this. I draw these other lines here, and one of the top line is 1 SD above average, and the bottom line is 1 SD below average. Okay? 1 SD. Okay? So I have a I don't know, strip there, which is average plus or minus 1 SD. What percentage of the points do you think are going to be in between those lines? About 68%, right? Assuming everything follows the normal curve, which if it's football shaped, it does. I'll talk about that more later. But sort of roughly, you think about 68% of the points are within 1 SD of the average. So if I draw that picture, I should get 68% of the points. So what if I do this? So I'm drawing the regression line in here. So regression line is in the middle. And suppose I go 1 RMS error above that line, 1 RMS error below that line. What percentage do you think is in there? Any wild guesses? Yeah, 68%. So 68% is going to be in between those lines, okay? So this is just a way of sort of building your intuition about what's going on here. The RMS error behaves a lot like the standard deviation, but what it does is the RMS error tells us something about the spread for the prediction errors for the distances from the regression line, whereas the standard deviation tells us something about the spread away from the average of y. So in this case, away from this horizontal line. So about 68% of the points are within 1 SD of the average. About 68% of the points should be within 1 RMS error of the regression line. Okay? So that's kind of the first step at sort of getting at how to interpret the RMS error. Think of it very similarly to how you would think about the standard deviation, but rather than deviations from looking at distances from the average or deviations from average, we're looking at prediction errors or distances from the regression line. Okay, so I just wanted to draw those pictures. And okay, so now I wanted to get into a little bit more of what I mean by football shape. So I wrote this up on the board last time, but I'm prepared now to say a little bit more about it. And I'm going to add just a little bit too. So first thing is linear relationship with no outliers. So I mentioned that last time. And I've drawn my pictures like that today as though it's football shaped. In order for the regression predictions to really make sense, you need things to be linear, because what you're trying to do with the regression line is to predict the average value within each strip. So like I said last time, if you have something like this and you try to draw a regression line through there, well, you're not going to do a very good job of capturing the averages within each strip. In this strip, the average is somewhere up there. It's not anywhere close to the line, right? Down here, average might be pretty far below, okay? So in general, if you have something football shaped, the graph of averages should follow a line. And if you have some weird shape that's not linear, the graph of averages won't follow a line, and regression is not such a good idea. So second thing is that x and y both follow the normal curve. And actually, incidentally, I mentioned, regression is maybe not such a good idea in this case. There are other things you can do. We won't learn about them in this class, but there are other methods of prediction you can do in this case, in cases like this. Regression is as a linear prediction. All the predictions are on a line. If you make some prediction that's not some prediction method that's not linear, would do a better job of capturing this. So there are such things, but we won't do them in here. Okay. So second thing is that x and y both follow the normal curve. And there's one part I said this last time, but one part I want to add is that it's also normal in vertical strips. I'll talk a little bit more about this in a minute, but just briefly what I mean by that is that if you consider all the y values corresponding to a particular x value, just sort of collect them all, right? If you have this x value, make a list of all the y values. If you make a histogram for the list of those y values in that vertical strip, those values will follow the normal curve. Right? So not only do all the x values follow the normal curve, not only do all the y values follow the normal curve, but if you restrict yourself to the y values just corresponding to one particular x value, those values will follow the normal curve as well. Right, so like I said, I'll talk a little bit more about that later and why that's interesting or important. The last thing is that the relationship is homoscedastic. The word homoscedastic roughly translates as same scatter or same spread. Homo meaning same, scedastic meaning sort of spread out or scattered. And this is also kind of a statement about the vertical strips. Same spread in each vertical strip. Okay, so on this last point, I'll talk about this a little bit more. It sort of doesn't look that way. It looks like the y values in the middle are spread out more than the y values towards the outside. So if you consider this to be, I don't know, heights of fathers and sons, fathers here, sons on the y-axis, it looks like if you have a father that's average, the son's heights are more spread out as compared to a father who is, 6'5" or something like that. The spread of the son's heights there looks like it's smaller. So this is I don't know if I would say illusion, but it's a consequence of having many more people near the center. Okay, and I'll describe this in a little bit more detail, but just as a quick thought, suppose there are many more people in the center, so you have a greater potential to kind of randomly get y values that might be 2, 3, 4 RMS errors from the center. So this picture describes the range of all the little dots everywhere. And if you have like a lot of people near the center here, there's potentially you could get values that are 2, 3, 4 RMS errors away from the center. Very rare, right? But if there's lots and lots of data, it could happen. Whereas out here, there aren't that many people, right? There aren't that many fathers 6'5". So you wouldn't expect maybe that you would see a great deal of variability. You would sort of observe a great deal of variability in the sun's heights in that range. Okay. So let me describe that in a little bit more detail. Suppose. Suppose we have 100 people from this class, just random 100 people from this class. And 10 people from another Stat 21 class. Okay, and there's no reason to I'm going to think about people's heights. Suppose there's no particular reason why tall people would be more likely to take this class than another class, whatever. So if you think about first the average height, so the average of this class we think it's going to be about the same as the average of the other class. I'm sorry, average of the 100 people. I'll say it that way. Average of the 100 people from this class. We think is roughly going to be the same as the average of the other class. They might be off by a little bit, but there's no reason to think that systematically one group should be taller than the other. Oops. So what about the standard deviation? I think that's slightly more subtle. Do you think that the standard deviation should be bigger in the group of 100 people or bigger in the group of 10 people? Or same? People say 10. Why do you think 10? Does anyone think 100? A couple people think 100? Anyone think the same? People think the same? Out of a handful of people that raised hands. Anyone want to say why intuitively you might expect, say average of 10 is bigger? Let's try that first. Anyone want to say why they think the average of the 10 should be bigger? You can be right, wrong. Doesn't matter. Yeah. There aren't as many people, so maybe it won't be that close to the overall average you're talking about? Okay. Any other thoughts? Yeah? Think it's for the 100? Why? More people farther away, so that might make you might have more people farther away, so you have a bigger standard deviation. Okay. Anyone want to speak for the same? Or yeah, go ahead.
For 10, the sample size is a lot less.
Uh-huh.
So the variation is a lot more.
For 10, the sample size is less, the variability is more. So then you think the variability is more? Okay. And anyone else want to say anything? Anyone want to say if they think that they're the same? Yeah.
Well, I think they could be the same if everybody in both classes are of the same height.
Yeah, so if you think that people are generally about the same height in each class, then you think maybe the variability is about the same. Okay. So they are the same. So there are a couple of common misconceptions involved in why some people think the SD of the 100 should be bigger or the SD of 10 should be bigger. So let me just address those really quick. It's not going to be exact. So these are, approximate. Both of these are approximately the same. It might be that randomly one standard deviation is bigger or smaller, but there's no systematic reason why one should be bigger than the other. Okay. Now let's think about why. The reason why is that the deviations should. I should be maybe a little bit careful here. There's a very slight technical there's a technical reason why this SD of 10 might be slightly smaller. Okay. And we'll address this in chapter 26, why that's true. But I don't think anyone's thinking of it, okay? This sort of technical reason why that might be smaller. So approximately, they should be very, very close. I think intuitively, the reason why they should be close is that there's no systematic reason. So the SD is measured in kind of typical distance from the average. There's no real reason why the people in one class should tend to be more or less spread out from the people in the other class. And the typical distance for, this is really measuring something about the individuals. It's measuring something about a typical distance for the individuals. So typical distance from the average for individuals, there's no reason to think why that should be bigger or smaller with more people or fewer people. Okay. Now I think part of the reason why some people think that the SD of 10 should be smaller is that, or the SD of 10 should be bigger, is that, sort of someone said, with fewer people you have more variability. There's an issue about how well a sample average estimates a population average. And we'll get into that in chapter 20, okay? And maybe a little bit beyond. But that's not really what we're talking about here. The standard deviation itself is not a measure of that. A standard deviation is simply a measure of the spread of those people. The spread of those people. How far are those individuals away from the average? Okay, yeah?
Does the fact that, like you, for the standard deviation, you do n minus 1 on the bottom, does that count? Is that the reason why there's some difference?
Yeah, so he's bringing up the technical thing that I am trying to avoid. He said there's an n minus 1 involved. So far, we have not addressed that. So far, we always use n's in the denominator of our standard deviation calculation, right? RMS, the deviation from average, is literally taking the square root of the mean of the squared deviation. So taking the mean is dividing by how many there are, divided by n, okay? And the reason why the book does it this way is because it's right. It's very common, I think, that people have this misconception that there should be an n minus 1 there in a lot of cases. And they don't understand it if they think an n minus 1 should be there, okay? Sometimes they're right. There are some calculations where an n minus 1 is correct. And we'll get into that in chapter 26. But typically what we're talking about here, if we're talking about a standard deviation, we're talking about the standard deviation of a list of numbers, okay? So the other issue is when you're using a sample average to estimate something from a population, and it's a different issue, okay? All right, so any other thoughts, questions about this? Okay, so yeah, these are equal. So hopefully you're convinced. Hopefully you're convinced that those standard deviations should be roughly the same, maybe a little bit off. Okay, so one more thing I want to mention about this. The tallest person out of all these 110 people, do you think the tallest person is more likely to be in the group of 100 or the group of 10? Any thoughts? Let's do it this way. Suppose I take 10 people here. Do you think the tallest person in class today is one of these 10 people, or do you think it's someone else, somewhere else in the class? You know, probably somewhere else, right? You know, it's not because these people are close to the front or anything, but just because there are lots more people, right? Lots more chances for the tallest person to be somewhere else rather than like right here. What about the shortest person here today? Do you think they're likely to be in this little group here or in the rest of the class? Again, probably the rest of the class, okay? So both the tallest person and the shortest person are probably in the group of 100 here. And I think that's part of the reason why someone was saying that they think the SD of the big group was, sorry, the SD of 100 should be bigger than the SD of 10. Well, because you're more likely to have these extreme cases. Problem is you also have more cases near the center. Not only do you have more extreme values, you also have more towards the center. In general, the distribution, or if you looked at a histogram for a small group of people and their heights and the histogram for a larger group of people and their heights, those histograms should look roughly the same. Same center, same spread. The only difference is that things are a little bit more filled out in the bigger group. So you might have a few more of these cases farther away. Like I was saying in this picture, you know, many people in the center, so you might have more people that are, you know, 3, maybe even 4 RMS errors away from the regression line in the center, whereas here, if you only have a handful of people, you know, kind of imagine my 100 people in the middle here, my 10 people in the middle here, same, you can think of this as sort of, well, in this case, they're not the same center because of regression, but the prediction errors are centered at this point here, the prediction errors are centered here, you know, here, and the size of the prediction errors typically should be the same in each case, okay? So bigger range for the group of 100, that does not contradict the idea that they can have the same SD, okay? So because the range is bigger, the picture does not look homoscedastic. It looks like it's fatter in the center, more spread in the center. But in fact, since this is just a statement about the range from the biggest to the smallest, range from the biggest to smallest out here, the range can be bigger in the center and still have the same, essentially the same SD, right? The same spread around the regression line. Okay, any questions about that? Okay, so it's a little bit of a subtle point. Mostly, I just want you to get the idea that, in fact, it is homoscedastic. That's part of what football shaped means. And that allows us to do some stuff. So, okay, so remember, the SD is originally defined as the RMS of deviations from average. And what we have is the RMS error in this case, in this regression context. Since the RMS error is the same in every vertical strip, because it's homoscedastic, what we essentially have is we have a vertical SD in each strip. So in any vertical strip. When we have a football-shaped scatter diagram. Okay? So again, the football shape tells us that it's the same spread everywhere, and the RMS error measures that spread. So now, what do we know about those points in there? We know their center is here, right? So this is, you might think of this as like a new average. We know their spread. You might think of this as a new SD. Okay? This RMS error measures the spread of those y values in that, just particularly to that vertical strip. And we know one other thing based on football shape. The other thing we know about these values is that they follow the normal curve. Okay? So if you just turn your head sideways for a second, look at that. We have a normal curve there, and we know the center. We know the average. We can calculate it using regression. We know the spread. It's the RMS error. When you know the average and then you know the SD of a list of numbers and you know that they follow the normal curve, what can you do? You know the average, you know the SD, you know they follow the normal curve. Yeah? Yeah, you can do a bunch of stuff. And in particular, the basic thing you can do is you can convert into standard units and use the normal table. Okay? So you can find percentiles, you can find percentage above a point, below a point, whatever you want. Basically, you can do things that are in chapter 5, right? So we know average of y values in a vertical strip. Right? We know SD. And they follow the normal curve. So we can use the normal table. Okay? So basically whatever is in chapter 5, converting into standard units, finding percentiles, whatever, we can do that in vertical strips. Okay? So I think I'll take a break there. This is important. This is like sort of a important end to a fairly long road, right? This is regression. This is the spread is RMS error, and there's this normal curve football shaped part. So I'll give you a second to digest that, and then I'll do an example. Okay? Okay, why don't I get started again? So I want to use this idea to do some chapter 5 stuff. So I'm going to go back to a data set that I have talked about a few times before, midterm and final scores. So midterm average is 71, SD is 12. Final average is 70, SD is 11, and R is 0.6. And scatter diagram is football shaped. Okay. So then what I'd like to know is of students who got 83 on the midterm, about what percent got above average on the final? Okay, so without doing any math, well, what do you think the answer is going to be like? If you get an 83 on the midterm, that's a standard deviation above the average. Any thoughts about how likely you think it is that you're going to get above average on the final? Anyone want to throw out a number, or just say like it's going to be bigger than something? Thoughts? Yeah. I don't expect you to be able to guess this accurately at all, just sort of intuitively. If it happened to you, what would you think?
I would think around, it's hard, like, I think around 60% maybe.
Okay, so he's throwing out 60%. More likely than not, you get above average on the mid. You know, I mean, you just sort of did well in the midterm, right? So you sort of figure, at least certainly it should be above half, right? It's more likely that you get above average on the final than not. Okay. So you know, just imagine this happens to you. You feel pretty confident going into the final. You'll probably get above average on the final. 60% seem high, low. Anyone? We'll throw out another number. No one? No one wants to guess? Okay. Well, maybe think of a number in your head anyway. The other reason I suggest doing this is that I think a lot of times people maybe think it's more likely than it is, maybe. If you do well on the midterm, certainly most people do well in the final also, but you know, with a sort of not too strong correlation, it might not be that likely. 60% is actually low. It's more likely than that, but certainly not a sure thing. Okay, so let's draw a picture. There's 71, there's 83. Average on the final is 70. So we're essentially talking about these people, right? The people that got 83 on the midterm, their final scores are in here. And if you want to think about this in terms, just geometrically in terms of the picture, it's the people that got below that point, right? So you can imagine that, you know, up here somewhere is the average in that vertical strip. Okay, so we'll calculate. We actually did that calculation before. I'll do it again though. So that's the kind of what I've referred to as the new average. It's the average y value, average final score in this case, corresponding to everyone that got 83 on the midterm. And there's a normal curve here, right? It's kind of hard to draw sideways for me, but okay. So roughly like that. So the normal curve of y values, and I'm curious about essentially what's the area down here. Okay. I said above average on the final. So I'm curious about the area above here. Okay. So let's redraw that. So that normal curve, redrawing it the usual way. Don't know the average yet, but I'll just label it new average, just kind of intuitively. There's the new average. That new average is certainly going to be above 70, so 70 might be down here somewhere. So what I'd like to do is convert 70 into standard units using the new average, which I'm going to find using regression, and then dividing by the new SD, which is the RMS error. Okay? So it's essentially the same standard units calculation that I've done before, except that I'm subtracting off the average of these final scores and dividing by the SD of these final scores. Okay? All right, so let's do the math. Any questions about the I don't know, intuition or big picture behind what I'm doing? Okay, so like I said, let's do the math. So first step, find the new average. So again, this is regression. First step of regression is to convert to standard units. I'll just write out the steps as I go. So 83 is 1 SD above average. Maybe you could see that already. Step 2 is to multiply by R. So I get 1 times 0.6 is equal to 0.6. And third step is to convert out of standard units. So remember that after you've done the second step here, this 0.6 means that the predicted Y value is 0.6 SDs above average. So we predict 0.6 SDs above average. I want to convert out of standard units. So 0.6, now we're talking about final scores. So as a final score, 0.6 SDs above average is going to be 76.6. Like I said, I did that Tuesday, so maybe you remember that number or recognize the calculation. Okay, so that's 76.6 there. New average here is 76.6. Again, the area I'm trying to find is everything above 70. Okay, so there's one more calculation I need to do, and it's fairly simple. I'll just squeeze it on the bottom here, I think. Find new SD. And this is the RMS error. Okay, again, since it's football shaped, I know that it's homoscedastic, so I have same spread in each vertical strip. That's the part I'm using here to get the spread in this vertical strip. Okay, so that comes out to be square root of 1 minus 0.6 squared times the SD of Y. SD of final scores is 11. That comes out to be 8.8. Okay, so new average is 76.6, new SD is 8.8, and I sort of want to leave the definition up there, so let me just move over here. So in this picture again, now I want to try to convert this value into standard units. So I take that value, subtract off the new average, divide by the new SD. So standard units is going to be 70 minus 76.6 divided by 8.8, and that comes out to be minus 0.75. Okay? So that's 70 in standard units is minus 0.75. So if I look that up on the normal table, I get 54.67. And roughly that's about 55. This is about 100 minus 55 over 2 is 22.5. And so our answer is about 77 and a little bit. So I'll say about 77 and a half. The area here, about 77.5%. Okay? So maybe, I don't know if that's higher than you sort of maybe thought in your head or not. Certainly most people who get 1 SD above average on the midterm should expect to get 1 SD above average on the final. I've mentioned correlation a couple times for big classes like this, and 0.6 is a little bit lower than usual, but sort of not that far off. Okay? So, so there you have it. If you're 1 SD above average on the midterm, that's about the percentage of such people that would get above average on the final. Okay, questions? Okay, so these problems, these vertical strip problems, tend to be a little bit long, right? You have to figure out how to convert into standard units. So you have to do regression to find the new average. You need to do the RMS error calculation, and then convert to standard units and do the normal curve stuff. I want to just highlight how I'm using all these parts of football shaped. The linear part with no outliers is required in order for regression itself to make sense, right? So in order for this new average to make sense, in order for that to actually be close to the average in that vertical strip, there has to be a linear relationship. Okay, so that's part of being football shaped. I'm not actually using directly the fact that x and y both follow the normal curve, but I am using the part that says also normal curve in vertical strips. So I'll just say as kind of an aside that it's also true in horizontal strips. You also get normal curve in horizontal strips, but we don't care. We're not going to really use that fact. So the fact that this looks like the normal curve and that we can use the normal table there, that's part of this second thing, normal curve in vertical strips. And then the third part, the homoscedastic part, that's what tells us the SD, this new SD makes sense, that the RMS error applies to just the points in this vertical strip. In general, even if it's not homoscedastic, the RMS error applies to the whole picture. So when I drew this picture before, just really quick, just this picture here, where I drew the bands across there and said 68% of the points within one RMS error of the SD, that's true anyway. Okay, that's true even if it's not homoscedastic. But in order to do the vertical strip part, you need the homoscedastic part. Okay, so this kind of long calculation actually uses all these parts of being football shaped. So it is actually necessary to have this be true. Okay, questions? Okay, so that's kind of the end of chapter 12. I want to go on to end of chapter 11. I want to go on to chapter 12. So I'm a little bit ahead, but I still think it makes sense to do this. Okay. Okay, so chapter 12 has to do with the regression line. And I talked a little bit about the regression line already, obviously. Let's see. Any questions about the example before I erase? Yeah? Okay. Okay, so chapter 12 talks more specifically about the regression line. It is a line, and since it's a line, you could write down its equation in the form y equals mx plus b. And I'll do that, but I'm actually going to write it just in a very, very slightly different way, which is to say predicted y is equal to mx plus b. And this word is important to me, the word predicted. I'll tell you right now, on exams, if you write down the equation of the regression line without including the word predicted, you'll lose a point, okay? So, it's that important to me. It's 1 point worth of importance to me. The reason why I sort of care about that is that I think that there's a important thought behind this line, which is that the predicted values using regression are on a line. The actual values are typically not on a line. So I feel like if you say this, what you're really saying is that if you plug in an x value into this equation, you should get an actual y value as your answer. And that's not true. The actual y values could be all over the place, right? But the predicted y values, they should be on the line. Okay, so that's part of the reason why I'm sort of emphasizing that that idea, that it's the predicted y values that are on the line. Okay. So how can we find m and b? Well, to find m is slope, right? So slope is equal to rise over run. So if you think about what's going on with regression, you know the point of averages is always on the regression line. So that's one point. And from the very beginning, I've sort of emphasized this idea that if you're 1 SD above average for x, so if I take a point here that's 1 SD above average, what should your y value be in standard units? How far above average do you think the y value is going to be? If you're 1 SD above average for x, you should be r SDs above average for y, right? If you think back to the math in this problem, midterm score, 1 SD above average. Predicted y value, 0.6. R SDs above average for y. The reason is this is multiplication, right? This is x in standard units. So if x is 1 in standard units, multiplied by r, predicted y should be 0.6 SDs above average. So the predicted y value here should be r SDs above average. So this distance should be r SDs. And they're different SDs, right? This is the SD of y, this is the SD of x. So the slope, rise over run, if we have a run, horizontal distance of 1 SD, that should correspond to a vertical distance, a rise of r SDs for y. Okay? So slope of the regression line is r SDY divided by SDX. And you can see it from this picture. Okay? Any questions about that? Why that makes sense? And if you forget, maybe you can kind of remember this idea that if you're 1 SD above average for x, you should expect to be, be predicted to be r SDs above average for y, and that gives you the slope. Okay. So B I'll find in 2 different ways. And you only have to learn one of them. I feel like showing you 2 different ways to do it. The book does it one way, and the way the book does it, I think is, it's fine. The book, I think, sometimes does things that make sense conceptually, but they're not necessarily the easiest way to do it. And that's the case here. So the book method is basically to think about what the regression line means. Okay? So go to my picture here, or I guess to think about what B means. B is the y-intercept, right? So if I continue this line all the way to the y-axis, this distance is B. Okay? So one way to think about B is it's the predicted y value when x equals 0. That's the way the book thinks about it. Okay. And you think about what the formula is, predicted y is equal to mx plus b. If you plugged in 0 there for x, you'd get a predicted value of b, right? So you can do this in a different way. You can just do the prediction. So you can use the regression method to predict y when x equals 0. So what you would do is convert 0 to SU, multiply by r, and convert out of SU. Okay? And that's just the regression method. For x equals 0. Okay, so that's the way the book does it. Like I said, that's perfectly fine. And this has the nice feature that you already know how to do this, right? You already know how to do the regression method. And it's not very long, so if you feel like doing it that way, that's fine with me. But I kind of like to do it a different way, which I'll call the point slope method. You might remember from earlier in your life in algebra or something that if you know the slope of a line and you know a point that's on a line, you can find the equation for the line. Okay? And we just found the slope up there. What point is always on the regression line? Point of averages, right? So that's basically the idea that I'm going to use here. And the way I'm going to write that is that, or think about that is, if I plugged in the average of x into that equation, the answer should be the average of y, right? If x is at the average, the predicted y should be at the average. Okay? So x bar is the average of x, y bar is the average of y. So like I say, if I plug in x bar here, my answer, my predicted value should be y bar there. So this should be true, okay? And I know m, it's r s dy over s dx. I already had to solve it for it before, so I can solve for b. Okay? So this is a little quicker. If you've already gone to the work of finding m, plug in the averages, solve for b. If you want to memorize it, I suppose you could. B is equal to y bar minus mx bar, if you want to throw that on the other side. I'm not even going to bother writing it down as a formula. I mean, writing it down that way because this is so easy to remember, right? Y bar equals mx bar plus b. You're used to thinking of a line as being y equals mx plus b. So just put bars over those. You got it, right? And then you can still just solve for b. So like I said, that's a little bit quicker, and it uses a little bit of information that you know that the point of averages is on that line, so it kind of reinforces that idea. Okay? All right, questions about that? All right, so let me do it both ways. I'll do it using the same data. All right, so I'll just write down the data again really quick. If you already have it in your notes, you don't need to bother if you don't want to. So midterm average is 71, SD is 12, final average equals 70, SD is 11, R is 0.6. I'll say it's football shaped again. Technically, if I want to calculate the equation for the regression line, there's nothing that says that it must be football shaped. I can happily calculate the regression line for something that's not linear. It's just that it won't be very useful. The regression line won't go through the averages in vertical strips, and it might not be a very smart method of prediction, but I can still do it. I can still find the equation for the regression line without knowing that it's football shaped. Okay, so anyway, let's do it. So m r times sdy over sdx comes out to be 5.5, or 0.55. So that gives me the slope, and I'll do b both ways. So b by the book method. So I need to convert 0 into standard units. So 0 minus 71 over 12. Gives me minus 5.9. So this is another reason why I kind of don't like the book method in a certain way. It's fine mathematically, it totally works, but negative 5.9 SDs below average is not really something that's going to happen in real life, right? That's really far away from where we would probably have any data. And in some cases, there's something a little bit nonsensical about, for example, predicting someone's weight when they're 0 inches tall, right? So in a lot of cases, plugging in a value 0 or using the regression method when x is 0 sort of doesn't make sense. In terms of solving and getting your answer for b, it'll give you the right answer, but it's just a little bit weird to be doing that prediction when there's not really any data there. you don't really necessarily believe that someone 0 inches tall will be -5 pounds or whatever, you know. But anyway, it gives you the right answer. So this is converting to standard units. Multiply by r, which is 0.6, gives you minus 3.54. And then finally convert that out of standard units. So negative 3.54 times the SD, we're talking about final scores now. So SD of 11 points on the final, plus average of 70 gives us 31, okay? So this is roughly saying that if someone got 0 on the midterm, you would predict that they would get 31 on the final, whatever that's worth. Okay, so finally, let me just erase that board and write down the equation. So predicted y is 0.55x plus 31. Okay, so that's an equation for a line. And if you wanted to then do further predictions of final score based on midterm score, you can do them pretty quickly once you get the equation. So that's one motivation as to why in the real world you might want to find that equation. Is if you're going to do many predictions, you can just plug in x's now and get y's without having to go through all the steps of the regression method. Okay, so let me do the point slope method. So b by the point slope method. I know that y bar, the average final score, must be equal to 0.55 times x bar, 71, plus b. Solving for b, I get b is equal to is that right? Yeah, b is equal to 31. So you know, if you just do the math, you'll get 31. Okay? So like I said, this is a little bit faster. If you want to find b this way, it's a little bit faster. You don't have to learn how to do it both ways. If you learn how to do it one way, that's fine with me. This will give you the same answer. Predicted y is equal to 0.55x plus 31. Okay, so that does the main math in chapter 12. So I'm a little bit ahead of the syllabus. I think what's going to end up happening is I'll do some stuff from I'll finish up chapter 12, do some stuff from chapters 1 and 2 on next Tuesday, and then I'll start chapter 13, probability, next Thursday, okay? So I know I just posted the syllabus, but I'm already a little bit ahead of it, okay? All right, have a good weekend.